Hello, this is part of the Controlled Environment Plant Production Engineering / Technology Education modules that were developed and presented by The Ohio State University, Rutgers University, and the University of Arizona, with support from the USDA NIFA program. This module discusses carbon dioxide enrichment and is brought to you by A.J. Both at Rutgers University, Cherry Kubota at the University of Arizona, and Peter Ling at the Ohio State University. The learning objectives for this module are that you should be able to understand the importance of carbon dioxide for plant growth, and you should be able to implement a carbon dioxide strategy and estimate the cost of adding carbon dioxide to a greenhouse environment. There are several additional resources that I think will be very useful. A publication by Nederhoff, a publication by myself, and a publication by Pete and Kryzak. Several of them you can find online, and the book Lighting Up Profits, Understanding Greenhouse Lighting can be purchased from Meister Media. Carbon dioxide obviously is very important for the process of photosynthesis. Plants use carbon dioxide and water and combine it with the energy provided by sunlight to produce the building blocks for plant growth and development, and also, of course, produce oxygen. But the important thing to remember is that this process is temperature dependent. So as the temperature changes and the plant environment temperature changes, this process goes faster or slower. Carbon dioxide is an invisible gas that is often overlooked when you talk about growing plants in controlled environments such as greenhouses. But despite the fact that it's overlooked, when the concentration is limiting, when the concentration is very low, it can have a significant impact on plant growth and development. So it's something that we really need to consider when we grow plants in controlled environments. And often, when you think about CO2 enrichment, so when we add CO2 to the greenhouse environment, we combine that strategy with adding supplemental lighting, because either one of them can be limiting in terms of the rate of photosynthesis. So we need to take a look at both of them to make sure that neither one of them is causing any problems to maintain a high rate of photosynthesis. To drive that point home, I want to show you this graph that was made from experiments done on lettuce plants, where on the horizontal axis you're looking at the carbon dioxide concentration, and in this case we use the unit of micromole per mole, which is equivalent to parts per million. On the left hand side you see, on the vertical axis, you see the shoot dry mass, so the amount of weight or dry mass that was accumulated in a period of 35 days from seed. And then the curved lines are representing different daily light integrals, the light sum that was provided to grow these plants. And so for lettuce plants, a typical weight that growers try to shoot for when they harvest their product and try to market it is about 5 ounces of fresh weight, which translate approximately to 7 grams of dry weight. So if you look at the horizontal line that represent the 7 grams of dry weight or dry mass, you can see that that line intersects these different curves for the different daily light integrals at different locations. And what that means is, for example, that if you grow lettuce plants at ambient CO2 concentrations, which is around 400 parts per million, at a light integral of about 16 moles per day, you get the 7 grams of dry mass in 35 days of growing. But you could also lower the daily light integral to 12 moles per square meter per day, and then if you increase the CO2 concentration to approximately 1300 parts per million or micromole per mole, you still get the same 7 grams of dry mass after 35 days of growing. So what this graph is telling you is that within limits, of course, you can try to increase the CO2 concentration, and as a result you don't have to add as much light to get the same amount of growth. And so this can be an interesting proposition if you're trying to save money, because typically adding CO2 is cheaper than adding light. So think about that and think about whether this may be something that you could implement for your crops as well. As I mentioned, the outside CO2 concentration is about 400 parts per million or micromoles per mole, and can be higher in locations where there's a lot of traffic, car traffic or people traffic. In an area where a confined area where a lot of people congregate, we can measure much higher CO2 concentrations than in well-ventilated areas, because obviously we expel CO2 as we breathe. We take in oxygen and we expel CO2. In greenhouses that are closed and not very well vented, and we have a lot of plants that are using CO2 for photosynthesis, we sometimes see concentrations drop to very low levels. And when the concentration drops below 200 parts per million or micromole per mole, we can see markedly reduced plant growth rates just because of that. And this is something that can occur on sunny days in the wintertime when we don't need to vent to maintain temperature. And the plants are obviously using a lot of light for photosynthesis and also require a lot of CO2 in that process. So under those conditions, we typically see low CO2 concentrations, and then it typically helps a lot if we increase the CO2 concentration, because it improves photosynthesis. Obviously, during the dark period, when there's no sunlight available, the plants are not photosynthesizing, but a process called respiration is occurring, which is more or less the inverse of photosynthesis. So in that case, plants produce CO2. So the equation that I showed you earlier for photosynthesis is reversed, and oxygen is used, and the building blocks of the plants are broken down to produce water and CO2. So during those times we typically do not have to increase the CO2 concentration because the plants are already producing it themselves. Most growers that do CO2 enrichment have looked at the rates of increasing and at to what levels, to what concentrations they need to increase the CO2 concentration to have a positive impact on plant growth and development. And by experimentation and by looking at the data, it is determined that doubling or tripling the CO2 concentration is typically adequate to elicit a positive result. If you go much higher than that, it's typically not economical because not all the CO2 that you keep adding is used by plants. The graph that I'm showing you here is explaining that under different light conditions, the effect of adding CO2 is different, and typically under higher light conditions there's more benefit of adding CO2 than under low light conditions. But if you look at the curves, you see that at some point the curves all flatten out. So even if we start adding more CO2 beyond those 800 parts per million or micromole per mole or so, you see that we see relatively little added benefit of that extra CO2. So you get the most bang for your buck when you are adding CO2 under lower light conditions, but under higher light conditions or under higher CO2 concentrations, you see that the impact of that added CO2 is leveling off. We also have to be concerned about the impact of CO2 on people working in greenhouse environments. Obviously the CO2 concentration that we are used to is not a concern and is relatively low, but as we are adding CO2 in greenhouses, which is an enclosed structure, we could see high CO2 concentrations. So when you reach a level of 5,000 or more, we start to get a little concerned. And so you need to have equipment in your greenhouse that can measure the CO2 concentration and raise an alarm when CO2 concentrations get really high, because they can have a negative impact and at some point actually cause significant problems for people working in those environments. The different sources of CO2 that we use for enrichment come from a variety of sources. They can come from combustion processes. When we combust fuels, we typically produce CO2 and water vapor, especially if we do that under good combustion conditions, optimum combustion conditions. Some cases there are some byproducts being produced, like ethylene gas or carbon monoxide. Under some conditions we need to purify the gases that come out of the combustion system to extract pure CO2 and then use that as the CO2 enrichment source in the greenhouse. But CO2 is also a byproduct of many industrial processes, so it's often readily available at a reasonable price. So it's something that we don't have to go out very far to find or to source. We often use CO2 in a compressed form because it takes up a lot less space when you compress it. Or we can even liquefy it, which takes even less space. But a liquid CO2 requires a refrigeration system, so that adds more costs to processing and storing the CO2. And then if you want to use a compost system, biomass decomposition, you can also generate CO2. And you also generate some heat, which could be helpful. So some growers use compost piles in their greenhouse facilities to generate some heat, but also generate carbon dioxide that can be useful for plant growth and development. But you have to be a little careful doing that, because if this process goes anaerobic without oxygen, then you can have methane production. And of course methane production can be dangerous if you get to concentrations that are combustible. So it's possible, but you have to be a little careful in how you do this. So if we use compressed or liquid CO2, which are one of the most typical systems, then we can convert that into a gas by releasing the pressure, and then we typically have a distribution system installed in the greenhouse. Very often there are small inflatable polyethylene tubes with little holes along the length of the tubes that we use to distribute that gas throughout the greenhouse environment. So sometimes you see those tubes, they're either inflated or not, depending on whether CO2 is being added or not in the greenhouse operation. One thing you have to remember is that CO2 gas is a little heavier than air, and so it tends to settle down to the bottom of the greenhouse environment. So sometimes we use fans, like horizontal airflow fans, to mix the greenhouse environment to make sure that the CO2 is evenly distributed throughout the environment. We can also generate, as I mentioned, CO2 by a combustion process. We have special burners that are specifically designed to generate CO2. They obviously also generate heat. So enrichment of CO2 occurs in this case at the same time as heating, and that may or may not be an issue if you don't want heat at the time you want to enrich. But anyway, these units are able to combust typically natural gas very cleanly if they are well maintained and well adjusted, and then they can release CO2 into the greenhouse environment. There are some challenges with these systems. They're typically installed overhead and sometimes close to energy curtains or shade curtains, and they have in the past become a fire hazard and have caused fires in greenhouses, and then that fire was spread when the energy curtains were not made out of a fire retardant material. But overall, you need to make sure that we produce pure CO2 with these systems. We don't want any of the byproducts such as ethylene or carbon monoxide, because they could both be harmful to plants as well as humans working in greenhouse environments. We do have additional heaters that are equipped with additional safety features, such as a outdoor air intake to prevent some of these safety issues from occurring. They also improve the overall efficiency, but again, they produce both CO2 and heat at the same time. So that may or may not be an issue depending on your particular situation and the application that you're trying to accomplish. The strategy that we follow to enrich CO2 is that obviously we need sensors. We need a way to understand what the CO2 concentration is before we know what we need to add or if we don't need to add. These sensors are relatively expensive and require periodic calibration. They don't maintain that calibration indefinitely, and so we need to invest in their upkeep and maintenance and make sure they work properly by calibrating them regularly. Once we have a good sensor and we can incorporate the sensing, the sensor readings into our control system, we can then use a manifold system with distribution lines and valves to distribute the CO2 gas in the greenhouse environment. So typically these CO2 enrichment systems are part of the control strategy, the control system we use to maintain the environment in greenhouses. And that is the way it typically works. We measure the environment, we look at light conditions, we look at other conditions, and we know the CO2 concentration, and depending on the target set points, we can then decide to, for example, increase the lighting, but also increase the CO2 concentration, because we know that the CO2 concentration is low when we were trying the light, and if we don't add CO2, that will result in conditions that do not result in the best plant growth and development that we were looking for. This slide shows you different types of sensors that we use to sense the CO2 concentration. On the left-hand side you have an analog sensor, and on the right-hand side you have a digital sensor. Again, I want to stress this, it's important that you calibrate these sensors regularly, so you need to introduce calibration gases at specific concentrations to make sure that the sensor is giving you the correct readout, and you need to do this regularly to ensure yourself that the system is working properly. We want to install these sensors, or at least their intake location, near the crop canopy, because we want to understand what the crop is sensing. We don't particularly care for CO2 concentrations either way below the crop or above the crop. We want to make sure that there's proper air movement around the sensor and around the intake of the sensor, so we get a representative measurement of what's going on in the greenhouse environment. And you want to understand that these sensors are sometimes susceptible to temperature fluctuations, so their output, their readouts, are susceptible to the temperatures in the greenhouse environment. And this could be a particular issue when your sensor is exposed to direct sunlight that heats up the sensor and then can throw off the accurate reading that you're trying to make with your sensor. So understand the impact of temperature on your sensor, and try to shield, if necessary, your sensor from solar radiation as much as possible to not have this become an issue in your operation. It's important to get an idea of how much it's going to cost you to enrich the greenhouse environment with CO2. And so on this slide I give you a very rough, and I want to stress it's a rough calculation for how much it's going to cost you to supplement the greenhouse environment with CO2. And some of the factors that influence this calculation are your source, obviously. How do you get your CO2? Is it a waste product that you get for free, or do you have to, for example, run your heaters and spend money on the fuel source? So what is the cost per unit of CO2? How many hours do you operate it? How much does the greenhouse leak in terms of air leakage to the outside environment? And how much ventilation do you do? How much air exchange do you do with the outside to maintain your temperature? Typically, when we do CO2 enrichment, we stop CO2 enrichment when the ventilation rate reaches a certain threshold. So a little bit of ventilation is typically acceptable when we start enriching, but at a certain rate of ventilation, it doesn't pay to add CO2 because most of it will be expelled immediately with the ventilation we are trying to impose to maintain temperature set points. So this calculation shows you then if you want to maintain an ambient concentration of about 400 parts per million or micromoles per mole, you would need about 50 kilograms of CO2 per hectare, which is 2.5 acres per hour. And so you can use that number by looking at how many hours during the day, an average day, you would use that enrichment, and the cost you'd have to pay per unit of CO2 you'd have to purchase or to produce. And then you can calculate how much it's going to cost you, for example, per unit area and per unit time to start enriching the CO2 concentration. So you can use examples like this and these ballpark numbers to get a rough estimates, but depending on your situation and the way you operate your system, you may find different costs for adding CO2 to your greenhouse environment. We'd like to acknowledge the funding that was received for this effort by the USDA NIFA program.